Some multiplication in the Hecke algebra can be done with wiring diagrams. Let's review how we use wiring diagrams to do multiplication in the symmetric group, and then look at the Hecke algebra analog. So in the symmetric group, we can use the wiring diagram of SI1 through SIR to multiply SI1 through SIR. So for example, well, that is, we take the unique path family. Let's say the wiring diagram is G. So we take the unique path family in G, in which two paths always cross when they have an opportunity. So for example, let G be the wiring diagram of S1, S2, S1 in the symmetric group S3. So the unique, let's say, always crossing path family is so I have a path from 1 to 3 because we have cross, cross, and then here we'll have a path from 2 to 2 because we have cross and cross, and then the last path family I'll just leave in blue from 3 to 1. This has type 1 goes to 3, 2 goes to 2, 3 goes to 1. Now we can also use the wiring diagram, the very same wiring diagram, to multiply E plus SI1, E plus SI2, etc. in the group algebra ZSN. So the sum of all types of path families covering G gives us the product in the group algebra. So if we use the same example, now this represents E plus S1, E plus S2, E plus S1. Now there's going to be 8 families of paths that cross this, because at every intersection we have a choice cross or don't cross, cross or don't cross, cross or don't cross. So let's write out all 8 of those. All right, maybe let's consider the 8 possibilities as integers 0 through 7 written in binary. So we could have no cross, no cross, no cross, no cross, no cross, cross, no cross, cross, no cross, no cross, 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 and then 4, 5, 6, 7, 0 through 7. All right, so no cross, no cross, no cross gives us a pathotype identity. No cross, no cross, no cross, no cross, no cross, no cross, 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 no cross, no cross, cross, no cross, 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 cross. Then the second path, got no crosses here. No cross, no cross, cross, no cross, cross, no cross, 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 no cross, 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 no cross, cross, cross. I guess I'll leave the other path in blue. So the types of these path families are 1, 2, 3, so that's E, and that's S1, and that one is S2. Here we've got, let's see, 1 goes to 2, 2 goes to 3, 3 goes to 1, that's S2, S1. 1 goes to 2, 2 goes to 1, that's S1. 1 goes to 1, 2 goes to 2, that's E. 1 goes to 3, 2 goes to 1, 3 goes to 2, that's S1, S2. And then 1 goes to 3, 2 goes to 2, 3 goes to 1, that's S1, S2, S1. So the product is 2E plus 2S1 plus S2 plus S1 S2 plus S2 S1 plus S1 S2 S1. Now in the Hecke algebra, I don't know of an analog of the first multiplication. Well, right here there might be an analog of the always cross multiplication in Sn. Maybe we can look at that together and see if we can figure it out. But I definitely know that there is an analog of the e plus si1 dot 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 e plus SIR multiplication, where we look at all the path families. No, we don't just record all the types of all the path families. We have to record a little bit more than that. Let's call an intersection of two paths defective if the paths have previously crossed an odd number of times. So for example, I've got all these path families here. I guess I can leave them here. Here we have two paths, the red path and the green path, that have crossed once. Then when they touch again right here, that's a defect. Let me circle the defect. And here these two paths have crossed once. Then when they cross again the second time, since they've previously crossed an odd number of times, that's a defect. These paths after they cross never cross again. These paths after they cross, well, never touch again. These paths after they cross never touch again. I guess we can't have any defective intersections between the second and third paths because they can't possibly touch twice. Now, using this idea of defects, we have a result about how to multiply the Q analog of what I'm just erasing. That is TE plus TS1 times TE plus TS2 times TE plus TS1. This theorem is due to Deodar. So let's let G be the wiring diagram of SI1 through SIR. Then we have the formula TE plus TSI1 product up to TE plus TSIR equals the sum of AV TV where AV is the sum of all path families pi covering G of type V, Q to the number of defects of pi, the number of defective intersections. So according to these 8 pictures we've drawn already, if we do this product here, TE plus TS1 times TE plus TS2 times TE plus TS1, we get E twice, once with a defect and once without. So we'll sum Q to the number of defects, Q to the 0th plus Q to the 1st. So 1 plus Q TE. And then we have S1 appearing twice, once with a defect, once with no defect. So we've got Q to the 0 defects plus Q to the 1 defects, TS1. And then all of the other path families appear defect free. So plus TS1S2 plus TS2S1 plus TS1S2S1. All right, now let's do the multiplication for real and see that this is actually the correct answer. I guess I will erase my pictures. So TE plus TS1 times TE plus TS2 times TE plus TS1 equals TE times TE times TE is TE plus, let's look at all the times where we take one basis element that's not the identity one. So we get TS1 twice and TS2 once. And then we look at all the products of 2. We get plus TS1S2 plus TS1 squared plus TS2S1. And then if we look at, I guess the only one left is TS1, TS2, TS1. Now as long as the product of the subscripts is a reduced expression in the symmetric group, we can just write it as a subscript here. But this one is not equal to TE, because according to the relations of the Hecke algebra, remember any generator squared is Q minus 1 times that generator plus Q times the identity. So this element is Q minus 1 TS1 plus QTE. So that means that our coefficient of TE is 1 plus Q. And then we've got Q minus 1 TS1s here and 2 TS1s there. If we add those together, we've got Q minus 1 plus 2 is Q plus 1 TS1. And then everything else, there's nothing else to combine. Plus TS2 plus TS1S2 plus TS2S1 plus TS1S2S1. So we can see that these coefficients of TE and TS1 match the coefficients of TE and TS1 that we got by using Deodar's formula. The end.